Okay, and the screen is visible to all of you?
Yes, sir.
Okay. Okay, so let's start today's class. So for the last few classes, I have been mostly discussing about transformation of electric field and magnetic field under Lorentz transformation. So how the electric field and magnetic field transform when you go from one inertial frame to other. But what I have not talked yet is the kind of object the electric field and magnetic fields are. Because if you look at electric field and magnetic fields, till now we have been treating them as vectors, right? Because electric field has three components, magnetic field has three components. So they are just three vectors. But what kind of objects they are in relativity, in four-dimensional space-time, that we have to understand. Of course, if you look at the transformation of electric field and magnetic field, they certainly do not look like the transformation of a four vector, right? If I let me just write down one of the transformation. So ex prime was equal to ex ey prime. I mean, for the kind of transformation where the prime frame is moving along the x-axis, ui minus vvz and ez prime equal to gamma ez plus vby. Now, this is certainly not the transformation of a four vector, right? First of all, we have three components here, no time components. Even we can guess that there could be a time component. That this transformation do not look like the transformation of four vector. So definitely, electric field is not a four vector, and so is the magnetic field. Then what are the other possibilities? Because we are in a 3+1 four-dimensional space-time. We have a four-dimensional space-time. So suppose if we assume that maybe just a minute. If we assume that suppose the electric field and the magnetic field are the components of the same object. So then we have to combine three components of electric field and three components of magnetic field, so altogether six components. So one may assume that it could be a sixth vector, but that is not possible because we have a four-dimensional space-time, right? Four-dimensional space-time. So we cannot have a sixth vector in a four-dimensional space-time. Then you have to work in six dimension, which we certainly do not have in relativity. Of course, mathematically you can go to any dimension, but in the real universe, when you talk about relativity, you have a four-dimensional space-time. Then what are the other possibilities? I mean, we have to explore that because electric field is not a four vector, magnetic field is also not a four vector, and they together do not cannot constitute a six vector at all. And now we are in four-dimensional space-time, and if we think in terms of say tensor, I mean, what is a tensor? Because you must have used I mean tensors in your other courses, and it's not definitely not new to you. So tensors are a mathematical object which can have multiple components. So if you are working in a particular dimension, say one dimension, two dimension, three dimension, and depending on the dimension, a tensor can uh, have how many components? Have I mean dimension to the power rank, So if it is a, so you are working in three dimension or four dimensions, say we are working four dimension, right? So four dimension, and if you have a rank 0 tensor, that means we have one component, right? That's a scalar, right? That's a scalar. If you are working with say rank 2, rank 1 tensor, this is rank 0, rank 1 tensor. If we have a rank 1 tensor, that will have 4 to the power 1. That's four components. So four components. We have four vectors. Example of rank 1 tensor. That's four vectors which have four components. And E and B doesn't fit into the kind of rank 0 tensor or rank 1 tensor. So the next possibility is go one step upwards. That means can we constitute a second rank tensor in four dimensions, say rank 2 tensor? How many components it can have? So we have R 4 to the power 2. That means 16 components. So a rank 2 tensor in four dimension will have 16 components. But if we combine three components of E and three components of B, three components of E plus three components of B, we have altogether six components which has to fit into a mathematical object. So right now we are just making guess that it could be some mathematical object which is a tensor of rank 2. So let us just explore this possibility. So we are not deriving it in a rigorous manner. We are just trying to look at the results which we have derived so far and try to figure out if this reconcile with the other results that we have obtained. So again, I'm assuming the same simple Lorentz transformation where the prime frame is moving along the x-axis with velocity v. That is the easiest one. Of course, you can assume any other transformation. Only the algebra will be more complicated. That's why I'm using the same transformation again and again. Well, so in that case, you have this lambda mu nu. The Lorentz transformation is gamma minus beta gamma 0 0 minus beta gamma gamma 0 0. So this is the usual transformation when the prime plane is moving along the x-axis. And now we have to, so you see scalar remains same, right? In whichever frame you go. For a rank 1 tensor, how it transform? For a rank 1 tensor, that we already know. See, if we have a 4 vector, that transform like lambda mu nu and a nu, right? A is a 4 vector. So in the prime frame, or maybe I can put a prime here if you like prime. So this is the 4 vector in the prime frame. So this is the in the 4 vector, same 4 vector in the unprime frame. So we can transform it by using this Lorentz transformation matrix. Now, what about the transformation of a rank 2 tensor? Because right now we would like to work with a rank 2 tensor, right? So a rank 2 tensor transform this way. So of course, you can assume that a tensor of rank 2, since in 4 dimension it has 16 components, so it's an object with 2 indices, right? So it's not only say a mu, it will be some, let us use some symbol, say f, that is the most familiar notation used for the field tensor. So right now I'm using f only. I could have used b or c also, but f, let us use notation f. F is a mu nu. So f mu nu is a second rank tensor. In the prime frame, you can connect this tensor. So this is suppose f say alpha beta. This is the same second rank tensor in the unprime frame, and we would like to relate this tensor with the same tensor in the prime frame. So for that, you have to use two matrix, Lorentz transformation matrix, lambda mu alpha and lambda mu beta, right? So this is the Lorentz transformation of a second rank tensor in relativity, right? And what shall we do with this? Okay, because we want to know whether we can obtain the transformation of electric field and magnetic field using a second rank tensor. So first of all, we have to figure out how can we fit these 6 components into a second rank tensor. So let us do that first. So how can we, okay, let us first write down general second rank tensor. Of course, if I have 2 indices, f say mu nu, it's a second rank tensor, some second rank tensor, general tensor. I am not talking about anything like electric field and magnetic. It's just second rank tensor. And the components are simply, you can see mu nu. So f mu and nu both runs from 0 to 3, 0 1 to 3. So f0 0, f01, f02. Along this, mu remains fixed, nu is changing. So f03. Then again mu changes. So f10 again, f11, f12, f13. Similarly, f20 for mu2 to 1, F22, F23, F30, 31, 32, 33. So 4 by 4 matrix. So it has a 16 components, 16 distinct components, right? Fine. But then we have only 3 components for electric field and 3 components of magnetic field. So how can we have a second rank tensor? So we can explore a little bit further. So suppose the tensor is symmetric. For example, symmetric. What is the definition of symmetric tensor? So for a symmetric tensor, f mu nu, if I have a for a symmetric tensor, for a symmetric tensor, f mu nu. So if you exchange the indices, it will be f nu mu, right? So altering the indices doesn't change the components, right? So that means, I mean, f10 and f01, they will be same, f20 and f02 will be same, and so on. So a second rank tensor, which is symmetric, I can write the symmetric tensor this way. So let us write down that again, f mu nu will be then f00, f01, 02, 03. But here, this will be on the opposite side of the diagonal. So this will be again same, because f mu nu equal to f nu mu. So this will be f01. They are same. f11 is the diagonal element, and we have f12, and then we have f13. Third row, you see we have already written f02. So this will be f20 is f02. This is f20, which will be f02. Then you have f12, this would be 21, but again they are same, so I'm writing f12, and then f22 and f23. Similarly, the fourth row, you see already we have f03, so f03 and f30 are same, so I'm writing f03 then, since they are exactly same. And we have the next element is f31, but we have already f13 here, so I'm writing f13. They are same again. Then we have f32, f23 and f32 are same, so I will write f23 and f33. So this symmetric second rank tensor in 4 dimension has now how many components? You see, I mean, they are same, f01, and these are same, right? So basically, how many components? 3 on the how many? 3, 3, 6. I mean, f01, and these diagonal elements are there, f00, f11, f22, f33. So all together now, from here we had 16 components, right? 16. Now we have 10 distinct components, right? From 16 we have reduced it to 10. For a symmetric tensor, we have 10 distinct components. But again, our problem is not solved, because we have from the electric field and magnetic field only 6 components. Then how can it fit in this symmetric tensor? It will not fit if you assume that the second rank tensor is a symmetric one. So for fitting it into a second rank tensor, you need to think that the next possibility is that maybe the tensor is not symmetric, it is antisymmetric. So if it is an antisymmetric tensor, so for an antisymmetric tensor, we have f mu nu equal to minus of f nu mu. So it is antisymmetric. So if you change the indices, I mean, you have a change in the sign here. So this is antisymmetric. And if it is an antisymmetric tensor, then if we write the tensor, the second rank tensor, then you see, since this condition has to be satisfied, that is f mu nu equal to f minus of f nu mu, so the diagonal element must have to vanish, right? You cannot have diagonal elements, right? So then so you are left with, you have 0, f01, f02, f03. Then you have minus of f01, this is 0, f12, and f13. This will be minus of f02 because just opposite and equal and opposite minus f12. Again, I mean the same matrix with the diagonal elements at 0, f12 and then f23. And then we have minus of f03 minus of f13 minus of f23 and then 0. So now you see we have only 6 independent component. You see 1, 2, 3, 4, 5 and 6, and these are the same value, right, with a negative sign on the other side of this diagonal. So now we have only 6 components, but that doesn't guarantee, guarantee that this will be something which will represent our electromagnetic field. This is just a possibility. We are trying to explore it, right? So since an antisymmetric second rank tensor has 6 components, let us put these 6 components of electric field and magnetic field into this mathematical object and try to see whether this can explain our electromagnetic field. So that is the next goal. And we already know how it transforms. See, so what we are going to next, you may have already guessed. So what I am going to do next, because since we know how a second rank tensor in 4 dimensions transform from one inertial frame to other, we will basically transform a second rank tensor from one inertial frame to other, and then compare this transform quantity, these 6 distinct components between the 2 frames, and then compare those equations with the transformation equation of electric field and magnetic field, which we have already derived from the transformation of Lorentz force earlier. So the transformation of a second rank tensor, okay, let us go to the next page. So we have now a second rank antisymmetric tensor with 6 components, okay, maybe so I have already written that, and the transformation equation which describes the transformation of this Lorentz this second rank tensor. So f mu nu prime is equal to lambda mu alpha f alpha beta lambda nu beta. So if you want, suppose I want to know what is f00 prime. So f00 prime, so if you keep mu and nu 0 and 0, and then keeping alpha equal to 0, change beta from 0, 1, 2, 3, then put alpha equal to 1 and then vary 0, 1, 2, 3. Mu and nu are fixed, right? So you have all these terms, right? You have to, sum over all this alpha beta, alpha 0 and then beta going from 0 to 3, alpha 1, then beta going from 0 to 3, and so on. So you'll have altogether 16 components. If you have to sum them together. But remember, this is something the common mistake is that, suppose if I write two Lorentz, so this second rank tensor is clubbed between 2 Lorentz transformation matrix. Now someone may wonder whether I can put the 2 Lorentz transformation matrix side by side and put this tensor at the end of this. That will not give you the correct result, because it is really not a matrix multiplication. That you have to understand, right? If you write it this way and use it as a matrix multiplication, that will give you correct result. So if you write down this tensor in between the 2 Lorentz transformation matrix and then multiply, that will be equivalent to the writing down all these terms, all this summation over all this alpha beta. It's up to you. It's your choice whether you want to use a matrix multiplication or you want to write down all the terms individually, by taking sum over alpha and beta. Both will give you same result. But the matrix multiplication is easier. Then you don't have to think about all those components in your mind. You just can multiply and get the correct result. So this should be clubbed between 2 Lorentz transformation matrix. Now, what was our f mu nu, which we have just proposed that? So let us write down the second rank antisymmetric tensor in the prime frame. So this is our object which we have in the prime frame. What is that? So it's antisymmetric tensor. All diagonal elements are 0. F0 F1 prime, say prime the prime frame, F02 prime, F03 prime. Then since antisymmetric, so F01 is a negative sign, this is 0, this will be F1 2 prime, F1 3 prime, F1 3 prime. Again this is antisymmetric, so 2 0 will be 0 2, F02 prime, this will be 2 1 and 1 2 are same, so minus of F1 2 prime, this will be 0, and this will be F2 3 prime, 2 3 prime. This one will be minus of F03 prime, second one will be minus of F1 3 prime, 3 1 and 1 3 are same, and this will be of course opposite to this, minus of F2 3 prime, this is 0. So this is the mathematical object of our interest in the prime frame, this one on the left hand side. So on the right hand side we have a similar second rank tensor which will be clubbed between two Lorentz transformation matrix. And in our case, the Lorentz transformation matrix is quite simple. This gamma minus beta gamma and so on. So it will be a bit lengthy. So gamma minus beta gamma 0 0 minus beta gamma gamma 0 0, and then this one the entire. So I have to write it many times, because if I want to do a matrix multiplication I have to write it, there is no other choice. F03 prime.
Sir, prime हुए
Oh, sorry. Yeah, yeah, you're correct. I'm just copying it, so without thinking. Correct. Yeah. F01, F02, F03, then minus of F01, 0, F12, F13, minus of F02, minus of F12, 0, F23, minus of F03, minus of F13, 2 3, 0, and then we have another matrix gamma minus beta gamma 0 0, minus beta gamma gamma 0 0. So this is a straightforward matrix multiplication. You just have to do it carefully, nothing else. Okay, so let us keep this first one intact, gamma minus beta gamma 0 0. Now let us do this. Okay, so row column, so this one 0 into gamma is 0 plus F01 minus beta gamma, so minus beta gamma F01, F02 into 0 0, F03 into 0 0. So this will be minus beta gamma F01. The first component will be minus beta gamma F01. First row, second column 0 0, F01 gamma F01, right? Other components will be 0, gamma F01. First row, third column, okay, only third element is there, non-zero, so it will be simply F02, F02. Okay, first row, fourth column, only last element is 1, so this will be F03, F03. Similarly, again, second row, minus gamma F01, minus gamma F01. Second one will be minus plus beta gamma F01, beta gamma F01. Other components will be 0, yes, second row, 0. And then again, second row, third column, only F12 will be there because there is only one non-zero term. And second row, last column, F13 should be there in the last element, F13, right? Similarly, let us take the third one. There are multiple non-zero things, so third one, 2 non-zero, minus gamma into F02, minus plus beta gamma F12. other two will be 0, right? 0 into 1 is 0. Sorry, 0, yeah, this one 0 into 0, 0, 2 are 0. So there are two terms, minus of gamma f02 plus minus plus beta gamma f12. And the second one again, there will be two term, minus plus minus. So beta gamma f02 beta gamma, no, f12, right? Which one I am doing? Let me make this one and this, yeah, minus of gamma f12. So beta gamma f12. এক মিনিট কি বললাম এটা, মাইনাস গামা f02 প্লাস বিটা গামা, ঠিকই আছে। তারপরটা কি হবে? Get correct. Just a minute. So the third one will be, just a minute, space is too little here to write down these things. It may look clumsy. Wait a minute. কোথায় গেল? So which one is this? Which one row? This one. I am working with third row, right? Yeah. Gamma f12. Yeah. So beta gamma f12 minus gamma f, sorry, beta gamma ভুল লিখলাম, beta gamma f02 beta minus plus, yeah, minus gamma f12 gamma f12, yeah. And then I have this one should be 0 and this one should be how much? f23 is only non-zero term, so this will be f23, right? And then the last row, minus gamma f03, okay, minus gamma f03, and then minus and minus plus beta gamma f13 plus beta gamma f13, and then we have this one, gamma minus plus beta gamma f03 f03, and then we have plus minus gamma, yeah, plus, and this is plus, this is minus, gamma minus gamma f13 minus gamma f13, and then this column will be, you have only minus of f23 non-zero term, so minus f23 minus f23, and this will be 0. Let us multiply this again. If I multiply this row versus column, so you can check it further. I mean, okay, because this is nothing more than the matrix multiplication. Everybody can do it. You just have to do it carefully so that you do not miss any plus minus sign, or you do not miss any terms. Okay, so I'm writing down this here. So maybe if I do it here, minus beta gamma square f01 plus beta gamma square f01. So the first term will vanish, minus and plus, you see, first term will vanish. Second term, gamma square f01 minus beta square gamma square f01 minus beta square gamma square f01. Third term, gamma f02 minus beta gamma f12. Fourth term, gamma f03 minus beta gamma f13. This one will be beta square gamma square f01 minus gamma square f01. Second term will be minus beta gamma square f01 plus beta gamma square. See, this one again vanish. The diagonal term, this will vanish, this will also vanish. Third one will be minus beta gamma f02 plus gamma f12. The last one will be minus of beta gamma f03 plus gamma f13. Third row, this will be minus gamma f02 plus beta gamma f12. This one will be beta gamma f02 minus gamma f12. This will be 0, this will be f23, and this will be again minus of gamma f03 plus beta gamma f13. Second one will be beta gamma f03 minus gamma f13. This will be minus of f23 as usual, unchanged, and this will be 0. You see, these two are 0, and so are these two diagonal elements. These are already 0, 0. This will be also 0. This cancels out, cancels out. So let us write down the matrix in the next page. So this prime matrix that we have, so let me again write down this one. So we started with this one, 0, this antisymmetric matrix f01 prime, f02 prime, f03 prime, minus of f01 prime, 0, f012 prime, f13 prime. This will be again minus of f02 prime, minus of f12 prime. This will be 0. This will be f23 prime. Antisymmetric, so minus of f03 prime, minus of f13 prime, minus of f23 prime, 0. And this equal to, we have calculated this using this matrix multiplication. So I am writing this simplified this one. So all the diagonal elements are 0. So you will have, if you come to this step from the previous page, the diagonal elements, they becomes 0, and the non-diagonal elements, so I'm just writing them in a simplified way, f01, and I'm just taking common, gamma common, in some cases gamma common data hobe, f02 minus beta f12. Once you do this, you will look some familiar things from here, gamma f03 minus beta f13. Can you recognize these things? You see, gamma times something minus beta into something, gamma times something minus beta into something. This remains, even without doing anything, you can guess, right? You see, this is unchanged, right? This could be the x component of electric field, right? This component, this could be y component of electric field, this could be the z component of electric field. Again, anyway, we will compare. This will be then antisymmetric matrix, so f01 prime, this will be 0, this will be gamma f12. So what I'm writing here is coming from the previous page. I'm just taking gamma common from both the terms. Gamma f13 minus beta f03. Antisymmetric, so I can write down this straight away, f02 minus beta f12. Second will be minus of gamma f12 minus beta f02, second one. Third one will be 0, diagonal element, this will be f23. And the last row, gamma f03, again it's an antisymmetric matrix, so I can write f30 equal to f03, beta f13. Second will be minus of gamma f13 minus beta f03. This will be again f23, so the minus of f23, this will be 0. Now you see, so f01 prime is f01, right? I'm just comparing term by term. f02 prime is gamma times f02 minus beta f12. f03 prime is gamma times f03 minus beta f13, and so on. So you can compare all the terms one by one, and then you can check what you see. I mean, whether that matches with your previous result, which you have derived from the Lorentz transformation of 4 force. Okay, let me just write down it so that it will be simplified. Uh, so I'm writing them. It is a straightforward f01 prime equal to f01. I'm just comparing the terms, components. F02 prime equal to gamma times f02 minus beta f12, and f03 prime is equal to gamma times f03 minus beta f12, right? And similarly f12, so we have 6 components of this antisymmetric tensor. F12 prime equal to gamma times f12 minus beta f02. We have f13 prime equal to gamma times f13 minus beta f02. I'm just comparing each of the terms. And f23 prime is same as f23. So even without thinking too much, you can just trying to guess, right? And you see that the things will match exactly. You see, if these are electric field, suppose maybe this can be also electric field, because in different notation, I mean, you can rearrange them in a different way. So for the first, try, let us think that we have seen that when the Lorentz transformation is applied along the x-axis, the x component of electric field doesn't change, right? So this could be our x component electric field. This could be our y component electric field. This could be our z component electric field. And if these are magnetic field, the component of magnetic field, then you can also guess. You see, this thing doesn't change, right? So f23 prime could be the x component of magnetic field, right? And then this will be the z component and y component, right? So how do I fit this into this, right? Can I use simply f01 prime equal to ex prime and f01 equal to ex? The answer is no, because you see there is a beta v by c, right? So if you want to compare your previous result, should I write it here? Maybe I can write it so that we can easily compare them, or maybe not, because it's very trivial. If I write ex prime by c equal to ex by c, that means if I take the first this f01 component as ex prime by c, not ex prime, it is multiplied with some factor 1 by c. That's identical. C will get cancelled and you will get the same result which you have obtained earlier. Similarly, the second equation, you can write this. So all these things will be just 1 by c times that. So uy prime by c, you see, this will be gamma. Again, f02 will be ui by c, because ui by c minus beta is what? V by c. Let us compare with our previous result, V by c, and then you have to say f12 is beta z, right? F12 is beta z. This is x component, this is z component, or on the reverse manner, x, y, and z component. So v by c, and let us call that the z component bz, and let us compare with your previous result. And let us write down this also. Ez prime by c is equal to gamma times Ez by c plus v by c, and sorry, this is minus or plus? Minus. There is this is antisymmetric, so v by c into by, right? So you can just compare. If you drop all these c terms from both sides, you see c drop c. So what you will get? Ui prime equal to gamma into ui minus dbj, which is exactly the same as our previous result. And if you drop c from both sides in the third equation, you will get z prime equal to gamma into z plus vby, which is exactly the same as the previous equation that we have derived from the Lorentz transformation of 4 force. We have not used any second rank tensor or anything like that. That was purely transformation of 4 force, because 4 force is a 4 vector which transform according to Lorentz transformation. And similarly, it's quite straightforward. You can see this is, if this is bx prime, so I can write okay, this is third term, because this is z. I told you that this is z. F12 is bz prime equal to gamma times this will be bz, then no 1 by c here. For magnetic field we are not multiplying by c.
স্যার
bj, bolo.
স্যার প্লাস বি বাই সি এটা কিভাবে বললেন? মাইনাস বিটা
কোথায় বলতো কোনটা?
স্যার F03 ড্যাশ যেটা ইজেড
হ্যাঁ হ্যাঁ
প্রাইম বাই
হ্যাঁ 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 তার মানে এখানে দেখো দুরকম রয়েছে না, এই যে একটা এই f12 আর f21, দেয়ার f12 আর এই কম্পোনেন্টটা আর f21টা দে আর অ্যান্টিসিমেট্রিক. দিস ইজ মাইনাস, রাইট? This is plus, this is minus. They're antisymmetric tensor, right? Okay, let me just complete this writing. Once I write down this all the components, then it will be clear. Okay, let me first write down them. V by C, V by C, and this is Ui by C. Assume Ui by C, right? And this is B y prime is equal to gamma. Second equation. এখন যখন মাইনাস হচ্ছে আমি প্লাস লিখছি ওখানে by plus V by C, and then what is that? Ez by C. V by C, Ez by C. তার মানে এটা অ্যান্টিসিমেট্রিক, মানে E02 আর E20 they have equal magnitude but the opposite sign, right? So V by C, Ez by C, and the last one is simply Bx prime is equal to Bx, right? So what I'm trying to show here is that we have obtained here the individual these are the six distinct components of the second ranked antisymmetric tensor that we have assumed. Okay, and we have obtained the transformation of the components, individual components, which are this, which I have written here, right? These are the transformation of the individual components of the second rank antisymmetric tensor that we have obtained here. Now, see what I am doing here. This is not a derivation from here to here. Then you will get confused. I'm not deriving this equation from this one. Wait and think a minute. Right? If you try to derive these equations from this, then you will get confused. I'm not deriving these. These are derivation. Okay? The underlying equations are derivation, right? That I have derived, right? And now I am comparing these results with the previously obtained result, which we have obtained by transformation of 4 force, right? So what I am trying to do is that I'm comparing equation by equation and trying to put different terms so that they can represent the 3 components of electric field and 3 components of magnetic field. Understand? So this is fine. So this is F12, right? But F12 will be equal to minus of F21. You get that? So that means some of the magnetic field component will be positive in this tensor, some will be negative, right? That means this is only indicating the tensor that we are going to obtain will have both plus minus sign. For example, the space time. So this is time component, no, right? Zeroth component, time component, and these are called time space component because these are mixed. I and j, mu and nu. Mu is a fixed. All the components which includes a zero are called time space or space time components. So these components, first one, second one, third one in the first row will be time space components. Similarly, all the elements in the first column, this will be space time components, right? Space time, because they also include some zero, right? And the rest of these components, these 9 components over there, these are called space components. Now what I am doing here, I am trying to compare this set of equation with previously obtained equation with some factor over there. So I am multiplying a 1 by c on the both side. That if I cancel c from both sides, I will get back my previously known equation, and this exactly matches with this one. If I assume that f01 is say ex, then that is fine. So whenever you assume f01 is ex, then f10 will be minus ex. F01 is ex by c, sorry, ex by c. That means f01 is ex by c. So this has to be minus ex by c, right? Similarly, if this is ui by c, then this has to be minus ui by c. If this is ez by c, so this will have to be minus ez by c. Similarly, for the magnetic field, they are not such symmetric. All the columns here, all of them are plus and all of them are minus. This will not be the exactly same for magnetic field. For magnetic field, you can look. You see F1, F01, F1, F01, this is F01 because they are same as F10. Then you have F11, which is 0, F12, and then F13, right? And what is, look at this, what is F12? Look at that. F12 is, you see F12 is what? F12 is nothing but magnetic Z component. You see F12, I have already labeled it Z component. But as soon as you write F12 prime as BZ, F21 will be minus BZ, right? So corresponding to this will be minus BZ. If this is BZ, this will be minus BZ. So this plus sign appears here because of this plus. So when you combine them, you see F1, this is not F21, right? For example, here, wherever you have a minus plus sign, right here, 1, 2, right? That means this will be, say, positive or negative f12, right? That means you have to make f21 as a negative. F21, if f21, that means if I put this one is minus bz, then this will be plus bz, right? So it is just, you have to rearrange, or you have to write down the terms with a proper plus minus sign, so that this two equation exactly matches with this two equation. So don't think that I am deriving this equation from this two set of equation. I am comparing so as to match previously obtained result. So this is a kind of comparison and trying to figure out, oh, so this is the same as the same object which you have obtained earlier. That means earlier we were treating 4 force, it's a 4 vector where we have used Lorentz force, which is again a 4 force. So that's a 4 vector which contains the term relating electric field and magnetic field, and that helped us to obtain the transformation for electric field and magnetic field. Now we are not thinking in terms of 4 force, we are trying to think the entire scenario in terms of a new mathematical object which we shall call electromagnetic field tensor, F mu nu, which has 6 components, 6 distinct components. It's a second rank antisymmetric tensor, and when we transform this second rank antisymmetric tensor under Lorentz transformation, the components, if you look at the transformation of the individual components, they exactly match with the transformation of electric field and magnetic field, provided we choose appropriate sign for these 6 distinct components. Is that clear?
Yes, sir.
Okay. So let us now write down F mu nu. See, I will also request you to note here. Probably you have used F mu nu in some other courses, right? So that is a very common, because if you want to write down Lagrangian, sometimes you need to write down in terms of using F mu nu. So probably you will use that. So in this discussion, what I'm trying to emphasize here, that F mu nu is something which describes an electromagnetic field in a complete manner. You don't have to think in terms of separately, like electric field, what is magnetic field. I mean, they are not separate things. That's an artificial thinking that we have been thinking for a long time, that electric field arises due to the say charge distribution and variation of magnetic field, time variation of magnetic field, or the magnetic field is the result of motion of charges or time variation of electric field. That is correct, but the thing is that all these things are not separate. They are basically components of a single mathematical object, which we shall call electromagnetic field tensor. And once we understand that, we can write down each and every equation in electrodynamics in terms of this electromagnetic field tensor, because that encodes every information about the electromagnetic field. If you know how to transform that from one frame to other, you can automatically get the transformation of electric field, all components of electric field and magnetic field. Further, we have seen that the magnetic field is a consequence of special relativity. It is not something separate where we think that, okay, motion of charge gives rise to magnetic field. That is fine, but why? That I have explained earlier, that why do you get something like a magnetic field, a new kind of force which tries to balance some other force which arises due to the motion of the inertial frame, right? So this is a consequence of relativity. So nothing surprising here. It has to happen, right? If the relativity is correct, if the assumption of relativity are correct, then there has to be something like this, which you call magnetic field. And this electric field and magnetic field, they are basically components of a single mathematical object, which we label as electromagnetic field tensor. So let us write down that. Okay, let me see how much time we have. Okay, another 10 minutes. So let us write down that F mu nu. Probably you have learned different form of F mu nu that I will discuss. Okay, there are some subtle differences. I mean, that's not physically, they are not different. So F mu nu, the way I have derived F mu nu is, this is 0, this is Ex by C, okay, Ey by C, Ez by C. This will be 0 Bz minus of By minus of Ey by C This will be minus bjets, and this is plus. As I told you, you could have put both of them is plus or minus, doesn't matter. But I mean, for the kind of thing we have obtained, this has to be taken plus, then this has to be minus 0, and then only you can match those two sets of equation. If you take this kind of sign, minus ez by c, the transformation that you have obtained by using transformation of this Lorentz force, and this second rank tensor, they will provide you identical result only if you take this form for the f mu nu, right? Well, I mean, you can see that, I mean, this is antisymmetric tensor from the sign itself. So sometimes in some textbook you will not see this c over there, right? So they put the things in a natural limit, so c equal to 1, so you have to then write down things accordingly. Or some people also use switch the position of e and b, but it has to be antisymmetric, and you see it has to have, I mean, only 6 components. You see ex, ey, ez, bx, by, bz, they are nothing but 6 independent components of this mathematical object f mu nu. And sometime also there is another tensor which is called dual tensor is defined with respect to f mu nu. And again, I tell you, this is not something very new thing, because this is this doesn't contain any extra or new information other than the things that are contained by f mu nu. So how do you get g mu nu? This is called dual tensor. Why? Because it is just for mathematical convenience. Don't try to find any meaning inside it. It's a dual tensor. It's a tensor which is called dual tensor. I mean, defined with respect to f mu nu. So if you replace all the electric field with magnetic field, so replace all E by C, replace all E by C with B, right? E by C with B, and all B with minus E by C. So this is just a I mean, manipulation. You just write E by C in place of E by C, you write B, and in place of B you write minus E by C. So whatever tensor you get is called dual tensor, and it has again 6 independent components, just like f mu nu. So if you do that, you will get 0 bx, by, bz, and then you have minus bx, 0 minus ez by c, because b has been turned to minus e by c, ey by c. This will be ey by c, this will be minus by, this will be ez by c, 0 and minus bz, minus ey by c, ex by c, and 0. So this is not some fundamental quantity. The fundamental quantity is f mu nu, which describes the electromagnetic field. And why we use this particular tensor? Because of the, I mean, it is easier. It becomes easier to write down the equation in terms of this f mu nu and g mu nu. That's mathematically convenient. That's why only you write this tensor g mu nu. Well, so we are now in the process of writing down all the equations of electrodynamics in terms of this field tensor. So that is our goal, because we are working in 4 dimension in special relativity. So we have to be able to write down all the known equation in terms of f mu nu. We will not think separately about electric field and magnetic field. We will only get bothered about by the quantity f mu nu from now onwards. So this f mu nu, you see, is a second rank tensor, right? Second rank antisymmetric tensor. Okay, it's a second rank tensor. And how do I get the covariant components of it? Because when we have a 4 vector, we got the contravariant 4 vector, like 4 velocity, 4 acceleration, 4 momentum, or any other 4 vector. We obtained the covariant components of it by just switching the signs of the spatial components, right? That was that we have already seen there. But how do we get the covariant components of f mu nu and g mu nu? So you may be aware how do you get the covariant components, because covariant components are obtained by using the metric tensor, right? So it depends on the geometry of space-time that you are using. If you are working on Minkowski space, so it has a well-defined geometry where you choose the signature of the metric. So how do you write this, right? So where am I here? So you write ds square equal to some c square dt square minus of dx square plus dy square plus dz square. Someone may choose to write, say, this is minus and this is plus, and that will not change any physics in your entire framework, but only the signs will alter. So in that case, that means this is ds square is what? This is g mu nu. You must have done the course in relativity, general relativity, so you know all these things, dx nu, right? So this g mu nu is called a metric tensor, and in this specific case, what is the signature? What is our g mu nu? For the Minkowski metric, it is 1 0 0 0 positive, 0 minus 1 0 0 0 0 minus 1 0 0 0 0 minus 1. This is our metric tensor in our case. Of course, someone may choose minus and then all plus, right? And how do you get a covariant components, right? If you have a, say, 4 vector, right, x mu or x nu, so how do we get a covariant component? So x mu, how do you get x mu? You just if you have, what do you do? G mu nu times x nu, right? That will give you x mu. So if you know g mu nu and if you know x nu, this is our, suppose, the 4 velocity, the contravariant components of 4 velocity. If you multiply with the metric tensor, you will get the covariant components of that same 4 vector. Similarly, how do you get the contravariant components from the covariant components? X mu equal to g mu nu, right? This one, contravariant x nu, right? But again, what is g mu nu? What is g mu nu? G mu nu is the covariant component. What is the g mu nu? If I ask you, what is g mu nu? The contravariant, the covariant, these contravariant components of the metric tensor. Can anybody tell? What is the relationship between g mu nu and g mu nu?
-1 1 1 1
একই স্যার, জি মিউ নিউ সমান জি।
একই
কারেক্ট জি মিউ নিউ সমান একই হবে। কেন একই হবে? ওয়াই? কেন একই হয়? আনসারটা কারেক্ট, যে এই দুটো একই হবে, রাইট, কারেক্ট। Because you see, what is this Gij? If I write Gij and Gjk, this will be Kronecker delta, right? Ki. So when k equal to I, this will be 1, otherwise it will be 0, right? So that means Gij equal to g mu nu equal to what? Gij and g mu nu, inverse of that. And since the inverse of the matrix is same as the matrix itself, that's why g mu nu and g mu nu are same. You see, this is the covariant, this is the contravariant. You multiply them. If k equal to I, that is Kronecker delta, it becomes 1. So covariant will be the inverse of the contravariant one. And since the matrix of this inverse of this matrix is same with the matrix itself, that's why they are equal, right? So the answer is correct. So similarly, it's what I have written is for the 4 vectors. So now if I ask you what is the, how do I get the components? How much time we have? Oh, we have passed our time. Anyway, I can continue my discussion from here in the next class. If you have any quick question, you can ask. Okay, so if you have no question, then you can continue the next class.